going to start with chapter 8, where we left off. So chapter 8 is going to be on hypothesis testing. So hypothesis testing is one of the major reasons that people do statistics. And if you recall back on the first day of the semester, we talked about the point of this class, the point of statistics, was to make a conclusion about the whole population using one or more samples. And already we've seen an example of that. And the example we saw of doing that was in confidence intervals, when we were making a conclusion about a population number by using a sample to do that. And we were able to look at the formulas for the confidence intervals to estimate a true population number using a sample number. Now, that example that we talked about was quite limited because we were only able to make a conclusion about a number for the population using a number for the sample. But now we're going to make a much more general conclusion about the population in the form of hypothesis testing. So, for example, let's say that you wanted to know whether a drug was effective in doing what it claims. Let's say in lowering cholesterol. And so, one thing that you could do is you could give the drug to everybody in the population to see what would happen. And what's the issue of doing that?
Fine. It would take too much time.
It would take too much time. Same issues as before, but now we have a new issue, a new problem in that example. And what would that be?
Safety concerns?
Yeah, safety concerns. So people could have adverse effects. People could die, and that's bad for business. So you don't want to just give the drug to everybody just to see what would happen. You want to give it to a smaller, controlled sample to see what would happen, and then generalize a conclusion from there. And so the conclusion then that we're interested in reaching for the whole population is not just a certain number like we did before with confidence intervals. It's a much more broad question, which is this drug effective? Which is a much more general question. So in hypothesis testing, we're answering much more general questions about the population using sample. And let's go ahead and use a very simple example to illustrate this point. And so let's say that we're walking down the street and we notice a coin on the ground that we pick up. And in our hand, it seems like the coin seems to be weighted differently on one side versus the other. So we suspect that maybe this coin is unfair. So our claim about this coin is that the coin is unfair. But what does fair or unfair really mean? So remember we said that if a coin is fair, that means that it has an equal chance of getting heads or tails every time you flip it. But equivalently, it also means that if you were to flip it a number of times that approaches infinity, like 1 trillion times, then the percentage of heads would be 50% if the coin were fair, and not 50% if the coin were unfair. But that would require flipping the coin a very large number of times, a number of times that approaches infinity. So let's say that you don't have the time or patience to flip the coin 1 trillion times to truly see whether the coin is at not 50% heads, so that you know the coin is unfair. So let's say that you still wanted to make this conclusion, but you didn't have the time or patience to flip the coin 1 trillion times. Then how do you think you could go about trying to answer this question about whether this coin in your hand is fair or unfair?
Flip a sample number of times.
Yeah, very good. So flip it a much smaller number of times, or a sample number of times, to find out this population conclusion. So let's say that we have this observation So let's start with saying, let's say we only flip the coin 10 times. So let's say we flip the coin 10 times, and we observe 6 heads. And in this sample of flips, 6 heads means that it's 60% heads. So does that mean that we can conclude that this coin is unfair?
No,
Yeah, why is that?
because the sample size is too small.
Very good, because the size of the sample is way too small, and you can imagine that even if you had a perfectly fair coin, you're flipping it such a small number of times that you can get a lot of variation here, and 60% heads for only 10 flips doesn't mean the coin is unfair. In the long run, this same sample could very well come from a coin that's actually fair. So 10 times is not a large enough sample size. So let's say that instead we flip the coin 100 times. And you could argue that that's still a small number of flips, but let's say that we only have the time or patience to flip it 100 times. And let's say that you flip the coin 100 times, and now you observe 55 heads. So the question is, what do you think you conclude about the true nature of the coin? Can you conclude that the coin is fair, or can you conclude it's unfair?
I think you could conclude that it's fair.
Okay. And of course you're gonna have some uncertainty in that conclusion. So let's say that your conclusion is that maybe the coin is fair. Because is there a chance that the coin is also unfair? Sure, so then your conclusion might be maybe fair, maybe unfair. So let's say that you had a second coin, and you wonder the same thing about the second coin. And so you have the second coin, and again, you flip it 100 times. Well, let's say the second coin that you flip 100 times, you get 90 heads. So, what do you think you can conclude about the second coin being fair or unfair?
Most likely unfair.
Yeah, so likely unfair. So, of these two conclusions with the two different coins, you're gonna have some amount of uncertainty in both conclusions, but which one are you gonna be more certain about? Which conclusion? Yeah, the second one. So this second one, you're gonna have more certainty in this conclusion. And why is that? Why do you have more certainty in the second conclusion? Yeah.
Because it is very far from the center.
Okay, very good. So
It's unproportionate.
So you're expecting, if a coin were to be fair, you're expecting, if you're to flip it 100 heads, you're expecting 50 heads. So this second coin is so far away from that expectation that you can conclude that that expectation can't be true. This observation couldn't have come from that model. So very good. So all hypothesis testing really reduces and boils down to this very simple example. So all hypothesis testing is that you have some claim that you're trying to test about the population. So here, you have some claim about the entire population of coin flips. So when we say the coin is unfair, we mean in the population of all trillion coin flips that we're not gonna get 50% heads. So your claim is always a population statement that you're trying to test. And in order to test that claim, we have an observation in the form of one or more samples. So here we had one coin where we had a sample of 100, we had another coin where we had a sample of another 100. So from there, we end up reaching a conclusion about the population. And the conclusion is gonna have some amount of uncertainty associated with it. So let's kind of try to deconstruct how we were able to reach our conclusions for each one. So because we're talking about according to being fair or unfair, we have this mental model in our mind. So, because we flipped the coin 100 times, we imagined that if the coin were fair, then our model would be how many heads expected out of the 100 flips for a fair coin.
50.
Yeah, 50. So our mental model is that we had 50 heads. And really what we were doing, most likely without being fully consciously aware of it, subconsciously what we were doing is we were comparing this observation of 55 heads to this mental model. And if it was close enough, then we said that maybe the model ended up generating this observation that we saw. So because these two are close together, the model of the coin being fair actually generated this observation of the 55 heads that we saw out of 100 flips. And it was because these two that we compared, the observation versus the model, because we compared these and they were close together, and so we concluded that maybe the model was true. And in this case, the model being the coin is fair, so maybe the coin is actually fair. So that's if the observation was, quote, close enough away from the model, then we can conclude that maybe the model is true. Versus over here, we had an observation of 90 heads this time, and again, we compare that observation to this model of the coin being fair, and we expected 50 heads. So in this case, we compared the observation to the model and subconsciously determined that the observation was too far away from the model. So because of that, the model could not have possibly generated this observation of 90 heads out of 100 flips. And so we conclude that the model could not possibly be true. So we conclude that the model was false. So model not true. And like we said, we have more certainty in this model not being true than over here when we said the model could be true. So all of hypothesis testing really reduces down to this simple situation where we have some claim about the population, we have an observation that we use to try to substantiate the claim, and we have some mental model that we're using to compare the observation to that model. And if the model is close to our observation, then we conclude that maybe the model is true. And if the observation is too far away from the model, then we can conclude that the model is not true with greater certainty.